So we have points on a square. The square has a side. And points can be on its perimeter, like this. And we want to find, we want to place at least k points such that the distance, Manhattan distance between them is at least some minimum value. So we want to maximize this distance, and we call it minimum distance of all of them. So, and we want to maximize it. And we want to return it. So this is a question of this problem. Now I didn't solve this problem myself. I was pretty close, but I did some mistakes, and I want to explain what those mistakes are. So the first is, let's think about solution. So the first idea is to navigate these points. So how can you pick them? How can you place these points? So we are given the 2D coordinates x, y of each point, but we want to know where each point is on this square. So my idea was to unroll into left, top, right, and bottom sides individually, and then concatenate them. So sort each of them. So for the left you sort like this in increasing order. For the top you sorting by x coordinate in increasing order. For the right by y coordinate in decreasing order, and for the bottom by x in decreasing order. And then concatenate them left, top, right, and bottom in a single list. The idea is kind of makes sense if you look at this at first, but this was a trap for me that led to the failure of my solution. I will shortly explain why, but let's go to the next idea. The next idea is how you can find maximum of minimums. So when you see this kind of maximum of minimums or minimum of maximums, the first idea is a binary search in your mind. Can you do this? Yes, you can do this. But what you should binary search for? Let's try binary search for the answer. The answer is maximum of minimum distance. So we're freezing the minimum allowed distance. So if we have this square and we have some minimum allowed distance, we will binary search it, but let's find out how we can check if it's accepted or not. So we have some points on the square, and if this if the pot distance between points is bigger than allowed distance, then that means we can take these 2 points. And if it's shorter, then we are not allowed to take this point. So this is how we can check it. Now we're going back to my first intuition, the first item of intuition where the trap was, and it's the checking if we can take or not. That was failed. I explain why. So let's just explain the working solution to not confuse the listener. So the working solution is you have to unroll this perimeter into single loop to calculate the distance. And the right way is that you have to consider the distance from 0, 0 in a perimeter path. So if you go on the left side, your distance is from 0 to S, where S is side. If you're on the top, your distance is from S up to 2S, and similar for the right, 2S up to 3S, and for the bottom, 3S up to 4S. Now this is a working solution, and then we just concatenate them, and this became unrolled increasing order of distances where we have some points. And this problem becomes not very hard. Just check if we can take these points with allowed at least distance. This is a minimum allowed distance, so it's allowed. The distance between points can't be less. Now, another interesting idea is, or I would call trap. You can't just start from the first point. You can't assume that this point would be ideal solution, because you have this wraparound distance from the last to the first that can be shorter than allowed distance. So you actually have to travel from each point and check every point. But if you travel and just blindly check collecting, that means you traveling n points in O of n, and then inside you iterating every point again, and this gives you O of n squared. But as our coordinates are growing, so we can use the binary search again, and to find the next position with minimum allowed distance. So imagine you have some points, you have some minimum allowed distance, and you just find the next point that is bigger, that have a distance or coordinates bigger. So if you're here on the first, you skip the second and you arrive at the third point. So this also binary search. Now another tricky intuition is how can you deal with this wraparound from last to the first. You can check your coordinate, so you can check your all travel distance. So if you collect some points together, imagine you collected these 3 points or these 4 points. This gives you some distance, and you can subtract from the perimeter, which is 4 sides, minus your collected travel distance from I, distance from the final position J, minus distance from the first position I. So this is like this, and you should check if it is bigger than allowed distance. So this is a final check. And the interesting fact is that the first my attempt, I concatenated these points together to have a simple wraparound check like this. But you don't have to, because if you have a winning subset of the points, and it happens so this subset in intersection manner, so you can say it's on the prefix and on the suffix of these points, and you skip it the middle points. You can say that you still can start with some point in this first loop, and if after you find this ideal point, all other points would perfectly lie on this first loop of the square. So you don't have to check twice. So if your first point and the last point has some good distance between them, that means all other points are in the first loop. You don't have to iterate a cycle twice, only once. Now let's look at the code. First, my accepted version. This is a big one, and I do this concatenation. If you concatenate that, then you have to do the duplication of the corners, and you still have to convert to the distances. So it's kind of ugly solution, but it was accepted. Now inside them I use this binary search outer loop, then I find the perfect starting point, and then I use while loop to count how many points I can take, and inside this while loop I use binary search to find the next point. So it's kind of trivial. Now let's look at the final Golf implementations. So this is a Kotlin one. Instead of concatenating, you can just convert, and the interesting part of this is that the distance is from the left and top edge is just x plus y, and it would be perfect distance from 0. And the distance from the 0 to bottom and right edge is the perimeter minus x plus y. So it's kind of interesting mathematical intuition. Then I sort them just by distance, nothing special. And this is outer loop. The interesting fact also for the highest distance of the binary search is the perimeter divided by k. So this is a perfect fit. Or you can just use perimeter, but divided by k is extra spicy. Now inside them I use any to check the perfect start, and I use the Kotlin built-in binary search. Inside binary search I use from index to make it a little bit faster. And if you use binary search, you have to invert if your index is less than 0, meaning this is the insertion point. Now, and I use do while loop, and I check the wraparound between the first and this I is the first and j is the last point. And I count how many items I take. So you also have to use longs because 10 to the power of 9 is kind of overflowing. Now let's look at the Rust solution. The same idea, different way to implement. I use collect vec from intertools and sort it. This is the same as Kotlin, x plus y, p minus x plus y, and the interesting way to find is trifold. You return sum, and if you return sum, it's would do search, and if you return value, then it is the answer. So, and also partition point is kind of more shorter than the binary search, and I use this slice from j, and you have to add j at the end. Also I used I64. So I think that's it for today.